everyone, and welcome back. Today we're going to be continuing our exploration of the analysis of real-valued functions and discuss the topic of continuity. So let's first off define what we mean by a function being continuous at a point. So we're going to be taking f to map the set A to R, and let's assume without loss of generality that the set A is indeed empty, in particular A belonging to A. So we say that f is continuous at that point if, for all epsilon greater than 0, there exists a non-negative delta, in particular also non-zero, such that the distance between x and a is arbitrarily small. For any x in the domain of a, the distance between f of x and f of a also must be arbitrarily small. So it's very important to analyze this definition from the perspective of limits as well, because the limit definition is also very similar to this, with the only couple differences between limits and continuity being that this distance cannot be equal to 0. Because if you remember about limits and its definition, the point A was a limit point of the set A. So A was not necessarily a point in that set. And also, this distance here is focused on the range element of A for f. Right? So there are those subtle differences, but nonetheless, these are very similar between one another. So using this definition, let's actually go ahead and do an example on how to prove that a particular function is continuous at a point. So let's look at the function f of x is equal to x squared plus 3x minus 5. And let's assume we're taking f to map the real numbers to the real numbers. And let's prove that this is continuous at the point, let's choose x is equal to 1. Right? So how do we prove that a function is continuous? So we're going to be letting, at least by definition, f of x to be equal to x squared plus 3x minus 5. And again, let's assume that we're mapping R to R. And let's assume that f of 1, or let's actually find f of 1, because we need to figure out how close we need f of x to get, or what number we need f of x to arbitrarily get close to. So f of 1 is going to be equal to, so we're going to have 1 squared plus 3 times 1 minus 5. So we're going to have 1 plus 3 is 4 minus 5, so that's going to be equal to minus 1. So we want f of x and minus 1 to be arbitrarily close to each other, as x and 1 gets arbitrarily close, in particular with respect to delta. Right? So what we're going to do is we're going to let epsilon be greater than 0 and see if we can find such a delta that makes this sequence true. So let epsilon be greater than 0. So what is the distance between f of x and f of 1? If we can show that we can make this arbitrarily small with respect to some given epsilon, then we practically have that f is continuous at x is equal to 1. So if we substitute our definition, so we're going to have x squared plus 3x minus 5 minus negative 1. That's going to be equal to the absolute value of x squared plus 3x, and then we have minus 5 plus 1, and we know that's going to be equal to minus 4. And we know that we can factor x squared plus 3x minus 4 over the set of integers, because that's just x plus 4 times x minus 1, and we can distribute our absolute values over that product and make it the absolute value of x plus 4 times the absolute value of x minus 1. Now, since we are having complete control over the distance between x and 1, that means we can control how big that distance is, right? So we know that that's going to be less than delta, so we just need to figure out, okay, how big does that delta need to be? But we do not necessarily control how large the absolute value of x plus 4 is. But if we know anything about the absolute value of x plus 4, what exactly does that curve look like? So x plus 4, the absolute value, is going to have a vertex at minus 4, and it's going to be increasing to the right and decreasing to the left. Right? So we are working around x is equal to 1. So when x is equal to 1, what is going on for this particular function? So when x is equal to 1, this function is equal to 5, So if we sort of build a neighborhood that we have complete control around, because we can make this distance as small as possible. When x is equal to 2, for example, this goes up to 6, and when x is equal to 0, this goes up to 4. Right? So when x is arbitrarily close to 1, this function, absolute value of x plus 4, is at most 6. Right? So we know that this is going to be less than or equal to 6 if x is approximately equal to 1. Right? So if that is the case, since we've already made x minus 1 arbitrarily small with respect to delta, then we can say that this is going to be less than or equal to delta times 4. And from here, it should be very easy to see what we're going to be choosing our delta to be, right? Because we know that, oh, that should be 6, not 4. 6, not 4. And that's going to be equal to what? So we want that to be less than epsilon, so we're going to choose our delta to be epsilon over 6, or something more smaller than that. And that's going to be equal to epsilon over 6 times 6, and that's obviously going to be equal to epsilon. So we have that as x minus 1 gets arbitrarily small, less than our chosen delta, then the distance between f of x and f of 1 is going to be arbitrarily small with respect to the epsilon that's provided to us. And therefore, what can we say? Therefore, formally, we can say that f is continuous at x is equal to 1. So that's how you prove continuity using the limit definition. The first theorem that is actually quite useful for the continuity of real valued functions is the following. And it says that f is continuous at x equals a if and only if the limit of that function at x is equal to a is equal to the function evaluation when x is equal to a. And since we're working with an if and only if statement, some people will actually even take this as the definition of continuity in single variable calculus, although it is not as rigid because it's not very easy to see that if we take this as the definition that, you know, the limit and the continuity are very closely related. But at least from the epsilon delta definitions, we clearly see that. So the proof of this theorem actually follows practically from the definition. So if that is the case, let's use this tool as an example to show that, you know, we can actually make a function continuous at x is equal to 2 as long as we control at least a couple parameters of our function definition. In this case, we have a function that's defined piecewisely, and we have this parameter k that we practically control. And this is very common in the realm of engineering and physics as well. So what values of k, and there could be more than one, is this function continuous at x is equal to 2? So we know that this function is continuous at x is equal to 2 as long as the limit of this function is equal to the function value when x is equal to a. So what exactly is the function value when x is equal to 2? So f of 2 is going to be equal to, well, this function is defined when x is equal to 2 for the first piece. So this is just going to be equal to 3 times 2 squared minus 5. So that's going to be 4 times 3 is 12 minus 5. That's just going to be equal to 7. Now we need to figure out if the limit of the function even exists and is equal to 7. So keep in mind the limit exists at a point if and only if the left and right hand limits of this function are equal to each other. And in this case, we are defined on the right and on the left of 2. So both the left and the right hand limits hopefully do exist. So let's look at the limits as x approaches 2 from the left-hand side of this function. So when x is to the left of 2, that means we're somewhere around like 1.9, 1.8, 1.7, somewhere near there. So that means x is going to be less than or equal to 2. So that means this is again going to be equal to 3 times 2 squared minus 5, and you can prove that with the limit definition for one-sided limits if you desire. But we already know that that's going to be equal to 7. And the limit as x approaches 2 from the right-hand side of this function. So when x gets close to 2 from the right, that means we're like 2 plus delta. So that's, you know, something slightly bigger than 2. So that means the second function is going to kick in. So that means this is going to be equal to k times 2 plus 2, and that's going to be equal to 2k plus 2. Right? So keep in mind, for these two limits to equal, implying that the limit does exist, that means that these two objects must be equal to one another in order for that limit to exist. So what value of k makes the limit exist? That means 7 must be equal to 2k plus 2, which means that 2k must be equal to 5, which means that k must be equal to 5 halves. So when k is equal to 5 halves, we have that the left-hand limit and the right-hand limit are going to be equal to each other. In particular, they're both going to be equal to 7. Therefore, if k is equal to 5 halves, the limit as x approaches 2 from the left of the function is equal to the limit as x approaches 2 from the right of the function, and both of them are going to be equal to 7. Therefore, again, if k is equal to 5 halves, the limit as x approaches 2 of this function will also be equal to 7. And we already have shown that f of 2 is equal to 7, and we know that the function is continuous if and only if the limit and the function value are equal to each other, and we know that they are equal to each other as long as k is equal to 5 halves. So when k is equal to 5 halves, we know that f is continuous at x is equal to 2 when k is equal to 5 halves, and it's not going to be continuous at x is equal to 2 for any other k that one can find. The next important topic that you definitely should know when it comes to continuity of functions is what we mean by a function being continuous on a set. So we say that f that maps a to r, so a is the domain of the function as usual, and let's assume that b is a subset of the domain of our mapping. So then we say that f is continuous on the subset b if f is continuous at all points a in b. Okay, so let's see if we can actually prove that a function is continuous, not just at one point, but infinitely points at the same exact time. So let's actually look at a very important example. Let's prove that f of x is equal to the sine of x is continuous on the entire set of real numbers, right? So that's quite a large set. Okay, so how are we going to provide a formal proof of the continuity of sine? Right? So let's be as formal as possible. Let's assume that epsilon is greater than 0. Then there exists a delta greater than 0 such that the absolute value of x minus a must be less than delta. And keep in mind, this is going to be true for all a in the set of real numbers. Then what do we have? So we need to show that the absolute value of f of x minus f of a must be less than epsilon without choosing a particular value of a in the set of reals. So what is f of x? So f of x is just going to be equal to the sine of x, and f of a is just going to be equal to the sine of a. Right? So what exactly is this? So what we have here is a difference of trigonometric functions, so we can use some of our trigonometric identities from pre-calculus in order to help us out here. So we can transform the difference of sine functions into a product of sine functions with our difference to product identity. So if you don't remember that, let me just state that here. So this is going to be equal to the absolute value of 2 times the sine of the difference, half, or the half of the distance. So 2 times the sine of half of the difference of x and a, half of the difference of x and a, times cosine of half of the sum of x and a. Right, so sine of x minus a over 2 times cosine of x plus a over 2. Right. So once we have this, then what exactly do we have? So we know that the absolute value of the cosine of beta is always going to be less than or equal to 1. So since x plus a over 2 is just a real number, and that's going to be true for any b in the set of reals, that means we can bound this above by 1. So that means this is going to be less than or equal to 2 times the sine of x minus a over 2. And also, if our function sine, so let's actually recall what sine function looks like. So this is a local version of sine, and this is a local maximum when x is equal to pi over 2. So when x is equal to pi over 2, that we know that this function is always less than, keep in mind that should be slightly above, it should be less than the function y is equal to x. right? As long as x is between, for example, 0 and pi over 2, right? So we always have that comparison. That's actually not too hard to prove with basic trigonometric principles, right? So if our beta belongs to 0 to pi over 2, that means sine of something will be less than or equal to something, right? So that's going to be less than or equal to 2 times the absolute value of x minus a over 2. So those 2's are going to cancel, and that means this is going to be less than or equal to, or actually equal to, the absolute value of x minus a. And we know that we control this distance completely because this is just going to be equal to delta, and then we can choose our delta to be our epsilon, and then we have the distance between f of x and f of a is arbitrarily close. So we have that if x minus a is between 0 and pi over 2, we have that this function is continuous, right? So therefore, if we have that f of x equals the sine of x is continuous, at least on the interval 0 to pi over 2, right? Now, how can we get the entire set of real numbers? So the rest of this is actually not too hard to show, but it comes from the properties of the function sine of x. So we practically already have continuity for this little piece, and we can get this little piece by symmetry around x is equal to pi over 2, and one can establish the continuity at x is equal to pi over 2 exactly, right? So by symmetry, f is continuous, and some people will write f as an element of continuity on the interval pi over 2 to pi. And you can also justify symmetry or odd symmetry on that interval as well, from minus pi over 2 to 0. And you can also justify continuity by mirroring that minus pi over 2 to 0 to minus pi over 2 to minus pi, right? So by symmetry again, we can get that f is continuous on the interval minus pi to pi. And that's just by symmetry. And how can we get the rest of the entire real line? Well, we know that the function sine is periodic. So we know that the sine of x plus 2 pi is going to be equal to the sine of x. And that's going to be true for all x in the set of reals, and that's by periodicity. Periodicity of the sine function. And the same can also be said for the cosine function. So that means that f is continuous on the interval minus pi to pi, union pi to 3 pi. So that's the next cycle on the right. And we also have minus 3 pi to minus pi. So that's the next interval on the left, and so on. Right? So we're continuous on the union of all of these intervals, and you should be able to see that that's precisely equal to continuity on the set of real numbers, right? So we have that the function sine is continuous on the real numbers. So that means sine of x is continuous on all of r. And that's at least one way you can prove formally that the function sine x is continuous everywhere. Right? Now, a couple other functions that you probably should also know how to prove that is continuous in all of r is the following. In particular, the first is constant functions, where constant functions, that constant can be any real number at all, 0, pi over 2, pi, and so on. You can also show in a similar manner that the function cosine of x is also continuous on the entire set of real numbers. And another very important function that you should know how to prove would be monomial terms x to the power of n, where n is a natural number, that all of these are continuous on all of r as well. Right? So I hope you enjoy those little proofs. So let's see what else we can actually do with continuity. So now that we know how to prove formally that a function is continuous at a point and also continuous on a set, now let's investigate what we mean by continuity of functions that are combined together. So the combinations of continuous functions. So let's assume that f and g are both mappings from the set A to the set R, with A belonging to A for, obviously for both of these points. So A is in the domain of both f and g. And let's also assume that f and g are both continuous at that point A. So we say that f and g are continuous at that point. This will also imply that the sum of f and g will also be continuous at that point. The product will also be continuous at that point. The quotient of those functions will be continuous at the point, provided that the bottom function is not 0 for all x in the domain. And also any scalar multiples of that function will also be continuous at that point as well. So what can we actually do with these theorems, right? So the sum of continuous functions is continuous. The product of continuous functions is continuous. Any scalar multiple of continuous functions is continuous. And this is actually really cool because you can build classes of continuous functions fairly quickly. So the first very important one is the following. So all polynomial functions, this practically is one of the more important results, are continuous, not just at a point, but they're continuous on the entire set of real numbers, right? So how can you prove that the set of polynomial functions, every single one of them are continuous at every single real number? So what we're going to do is we're going to choose an arbitrary polynomial p, and let's suppose that p is expressible in the form the sum from k is equal to 0 to m of akx to the power of k. Let's assume that its leading coefficient is not equal to 0, and let's assume that this is a degree n polynomial. And let's assume that each of those coefficients are real numbers for k is equal to 0, 1, 2, all the way down to n, obviously with the leading term non-zero. So what do we already know? So the first thing that you need to do to justify that all polynomials are functions is the following. The first is that f of x is equal to xn is continuous on the set of real numbers, and that's true for all natural numbers n. Now, keep in mind that that takes care of x to the 1, x to the 2, up to x to the n. It doesn't necessarily take care of that constant function. So you also need to be able to show that this function is also continuous on the set of real numbers for some constant c. So once you have that, then by the theorems of addition and subtraction, and also scalar multiples of continuous functions, since that's practically all what this is, right? Because, ak could be positive, it could be negative, and we're just adding up those continuous functions from the constant all the way up to the higher order term x to the m. Then we have that p of x belongs to the set of continuous functions on the set of real numbers. So the proof of that is not actually quite hard, as long as you have established that x to the n is continuous, c is continuous, and any linear combination of continuous functions will also be continuous as well. Now another set of functions that would be continuous would be the set of rational functions, which I'll denote as r of x. So keep in mind, a rational function is one that can be expressed in the form p of x over q of x, where p of x and q of x are both polynomials. And these polynomials can be of different degree. They don't have to match. So let's assume or specify that the degree of p is equal to, say, m, and the degree of q is a degree n polynomial. Right? And obviously, sometimes you can have a degree 0 polynomial. Keep in mind that would just be a constant function. If q of x is a constant function, then p of x is a polynomial, and that goes with the previous example that I just mentioned. And it's possible that p is also a constant function, q is a constant function. That's trivially a constant function, provided q is not 0. So, we practically get it. So how can you justify that r of x, rational functions, are also continuous at r, provided that it's defined? So, by the fundamental theorem of algebra, what do we know about the fundamental theorem of algebra? There exists some numbers, let's call them x1, x2, down to xr, in the set of real numbers, such that q of xk is equal to 0, where k is equal to 1, 2, down to r, with r less than or equal to n. So I'm looking at the distinct zeros of my denominator function, right? So as long as that function is non-zero, then by the quotient identity for continuous functions, f over g of x is continuous as long as q of x is not equal to 0. So by that theorem, we have that. So by the theorem of continuity of f over g, we have that r of x is continuous. So it's continuous. That's a funny looking C. So it's continuous on the set R except for x1, x2, down to xr. Right? So that's actually pretty easy to justify, as long as you have justified that the quotient of continuous functions is continuous, provided the bottom is not equal to 0. The last theorem that I want to mention in terms of the basics of continuity of real-valued functions revolves around the idea of composition of functions. So if you don't remember what the composition of functions, let's just do a quick review of what we mean by that. So let's assume that f is a mapping from a to b and g is a mapping from b to c. And let's assume that the range of f is a subset of the domain of g. Then the composition of g with f, sometimes represented with g circle f or g circ f if you're typing that on like LaTeX or something, is the mapping from a to c, which is defined as using the outputs of f as the inputs of the function g for all x in the domain of f. Right? So that's what the composition is. So let's just draw a picture just to make sure you understand what this is. So we have the set A, we have the set B, and we have the set C. And we have f that goes from A to B, and we have G, which goes from B to C. And let's assume that we want to sort of skip B, at least indirectly, and we want to just go from A to C. So the function that goes from A to C is not f composed with g, but is g composed with f. Right? Because f maps A to B and g maps B to C. So g of f maps A to C. Right? So make sure not to get those orders backwards. Right? So that's what we mean by the composition of functions. So let's state the theorem that talks about the continuity of the composition of functions. So theorem 3 says the following. Let's assume that a and b are both subsets of the real numbers with f mapping, again, a to the set of real numbers, and g mapping the set b to the set of real numbers. And let's assume that f of a, the image of a under f, let's assume that's a subset of b. So f of a can be viewed as the range of f. Then f is continuous, then if f is continuous at a in the set of a, and sets 1, 2, g is continuous, so g is continuous at b, which keep in mind is just f of a, and the set of b. If both of these things are true, then g composed of f will also be continuous at x is equal to a. Right? So that's how to prove that a function is continuous. The composition of functions is continuous at a point. Right? So what do we need? So we need a mapping f mapping a to r, we need g mapping b to r, and we need, now this is actually very, very important to stipulate, right? Because if the image of a under f is not a subset of b, then it's not going to be it cannot map to anything under the mapping of g, right? Because that point f of a is not necessarily in the domain of g, right? So it's very important that f of a is a subset of b here. Right? So that's usually the first thing that we check off. And then we have to make sure that f is continuous at a. We need to make sure that g is continuous at f of a. And once we have those three entities verified, then we can say that g composed with f is continuous at a as well. right? So let's actually work through a numerical example just to make sure that we can do this. So let's assume that we have f of x, which is equal to x squared plus 1, and let's assume that we have g of x, which is equal to x squared plus 5. So is g composed with f continuous at x is equal to 2? So is g composed of f continuous at x is equal to 2? So let's see if we can prove this. So what we're going to do is we're going to take the domain of both f and g to be the set of real numbers. So let's take the domain of f to be equal to the set of real numbers. So if we take the domain of f to be the set of R, what's the range of f, right? So this is very important. So keep in mind x squared plus 1 is just a parabola facing upward shifted up 1 unit. So note that the range of that mapping is going to be equal to 1 to infinity, right? And let's also take the domain of g to be equal to the set of real numbers. So the only thing that we do not need to know the range of g here. We just need to know that the range of f is a subset of the domain of g. That's all we need in order to compose g with f, right? So we see that the range of f, 1 to infinity, is a subset of the set of real numbers. So the first criteria is met for composing g with f. Now, if you want to do f with g, then you have to find the range of g and make sure that that's a subset of the domain of f, right? But you should be able to see that that's also true as well, but we're just focusing on g composed with f, right? So the first criteria for compositions and continuity is met. So let's check the other things. So keep in mind f must be continuous at x is equal to the point of interest 2. And that's obviously true because f is a polynomial. But what is f of 2? So f of 2 is equal to 2 squared plus 1, which is equal to 5. And we need to make sure that g is continuous at f of 2, which is 5, right? So what about g? So g is continuous at x is equal to 5. Because it's a polynomial, therefore it's continuous on R, and 5 is an element of R, so that is satisfied, right? So those are our 3 criteria. So we have that the range of f is a subset of the domain of g, that's our first. We have that f is continuous at 2. We have that g is continuous at f of 2, right? Because keep in mind that's just f of 2. That means what? That means the function g composed of f. Let's actually state what this function is. This is just going to be g composed of with f, and that's going to be what? So what is f? F is just x squared plus 1, and g is something squared plus 5. So something squared plus 5. So since we've checked out these 3 entities, we have that this function right here, which is a degree 4 polynomial, once you expand that out, this function is continuous at x is equal to 2, right? So that's how you can practically prove the continuity of compositions of functions. Notice that actually I don't even need to specify what this function is or even investigate it. I can actually just trust f and g on their own without actually explicitly finding what g composed with f is. So that's where this theorem sort of has its bright side. Right? But those are some of the basics associated with the continuity of real-valued functions. So what did we do today? We proved that a function is continuous at a point, or potentially not continuous at a point. We showed how to prove that functions are continuous on a set, and we discussed a couple little bit of algebraic properties of continuous functions with other potential continuous functions. And there are several little corollaries and special cases to consider. You know, is it possible that you have 2 discontinuous functions, you add them together and you get a continuous function back? Like, there's several different fun conversations to be had around that point. But again, there's more advanced techniques and topics associated with continuity that we'll get to at a later time. But until then, I hope you enjoyed this video. Take care.